So now we're going to talk about
So in this
descriptive
lecture, we'll talk
statistics
about
and
descriptive
sampling.
statistics and sampling.
And there are, so we can use either numerical summaries, tabular summaries, or graphical summaries
So
to
first, we're
describe
going to talk about
variables to
some different ways
summarize
that we might
data sets.
summarize the data that we
We
have.
can use the mean, median,
So we'll
and
talk about
range.
numerical summaries, tabular summaries, and graphical summaries. And the type of summary that you will use for the particular variable that you want to summarize depends on the level of data measurement. And so here are the four main categories of data measurement that we'll be talking about: dichotomous, nominal, ordinal, and continuous. So those first three come under the umbrella of categorical variables versus continuous variables. So when you're dealing with continuous variables, you have a variable that can fall anywhere on a continuum, hence the name continuous. For example, any kind of lab values like serum glucose, your anthropomorphics like height and weight, things like that, can be theoretically anywhere from 0 to infinity, although of course there's physiological boundaries as to what's possible. But they can fall anywhere on a continuum. They're just a number. That's a continuous variable, as opposed to a categorical variable that can only assume certain discrete values. Examples here you see are gender, ethnicity, what county do you live in, a tumor stage. Those are all categorical variables that can only assume certain discrete values. So normally when you hear about this in textbooks, when they talk about continuous variables, they talk about either ratio or interval level continuous variables. And I just wanted to kind of mention it because you might hear it, you might have heard it before. But when it comes time for analysis, that distinction between ratio and interval level data is not very important. But I just wanted again to let you know about the difference, so you've heard it. So if you have a ratio continuous variable, then the 0 means something. For example, age 0 is like maybe defined as when you were born, or if we're talking about temperature in degrees Kelvin, ratio that's a ratio level measurement, because the 0 means that's when the molecules stop. It's absolute 0 when you're talking in degrees Kelvin, as opposed to interval level, degrees Celsius, degrees Fahrenheit. Those are measures of temperature at the interval level, because the 0 is not really meaningful, especially in Fahrenheit. I don't even know where the 0 comes from. Does anybody? I don't know. But in 0 Celsius, at least it's the point where water freezes. But still, that's arbitrary, because it's you can go below 0, as opposed to Kelvin, where that is a ratio level measurement, because it's the point where the molecular movement stops, and you can't have a temperature below 0 Kelvin. But as I said, when we're talking about analysis, so for the practical aspect of this, you need to be able to group your variables into these categories to decide the appropriate way to analyze your data that we'll talk about later in the semester. So if you can just, if I give you an example of some variable, you need to be able to figure out which of these four categories, which of these four levels of data measurement your variable falls into. And then it'll help you to figure out how to analyze the data and how to summarize the data, is what we'll be talking about in this lecture. Okay, so we talked about continuous variables, ratio versus interval. So now let's talk about categorical variables. So that's the first distinction. Is my variable, is it a continuous or categorical? And if it's continuous, then that's that. But if it's categorical now, you need to decide among these three types of categorical variables. Is it dichotomous, nominal, or ordinal? So you might recall we talked about dichotomous, which is also sometimes called binary. And it's any variable that just has two levels: yes or no, present or absent, dead or alive, disease or no disease, male or female, etc., etc. So any variable that only can assume one of two values is a dichotomous or binary variable. But if there are more than two values, then you have to decide if this categorical variable is either nominal or ordinal. So the distinction, the way to think about this is from the name. I think nominee would be Latin for name, something like that. Whereas as opposed to ordinal implies order, ordinal. In other words, a nominal variable, the categories are just names with no inherent order. As opposed to an ordinal variable, the categories do have an inherent order. Examples of a nominal variable could be something like ethnicity. Caucasian, African American, Asian, Hispanic. Those are just names with no inherent order. So ethnicity would be a nominal variable, as opposed to something like tumor stage, 1, 2, 3, 4, or BMI category like underweight, normal, overweight, obese. Those are categories that have an inherent order. So that's how you would distinguish nominal versus ordinal. And you see that BMI there, BMI category is red because the actual raw BMI is a continuous variable, isn't it? It's just a number. You could be like 28.7 could be your BMI. But we convert those to categories sometimes in an ordinal BMI category. Okay, so that's talking about levels of data measurement. So now we're going to talk about some different ways that we could summarize our data using graphs. So here are some of the ways that we'll talk about in this lecture, but there are a lot of other different graphs that you can make. We talked about, we did control charts before, and that's a whole, could be a whole lecture or a whole semester into itself maybe. But talking about some other commonly used ways to display data. So let's just take as a motivating example. This is I've scanned this from Fundamentals of Biostatistics textbook by Bernard Rosner. It's like 100 consecutive births at Boston's Children's Hospital, and this summarizes them going from lightest to heaviest births. So you see here at the top the 32. That's 32 ounces, and there was one baby that weighed 32 ounces, the lightest. In fact, by far the lightest, because the next lightest baby was 58 ounces, and there was one of those, and 64 was the third lightest, etc. Come up, there were two that were 85 ounces, and so it's read like that, and three that were 89 like that. So here we have the birth weight, and then how many had that birth weight, and they are sorted in ascending order from the lightest birth weight up to the heaviest birth weight. And now I'll go to the next slide, and you'll see at the end the heaviest was 161. A baby weighed 161 ounces, and we had a total of 100 babies in this little sample of data. So that's just something we're going to show, like how maybe we could summarize this birth weight data. Some different ways to summarize the birth weight data. So one way would be to make a frequency table. The frequency table, like the first column tells the interval width, for example, the birth weight width, and we're going to have different intervals of the birth weight. The second column tells how many observations fall in that interval. And then sometimes, but not always, you'll have a column that is percent of total and cumulative percent of total. So here's an example. If we make a frequency table of that birth weight data that we saw before, you can see like there were 5 babies that were born with the birth weight in the interval of 29.5 to 69.5 ounces, 10 who were born in the interval of 69.5 ounces to 89.5 ounces, etc. And then up here, like at the heaviest, there were 6 who were between 139.5 and 169.5 ounces. This is a frequency table that could summarize those 100 consecutive deliveries birth weights. Okay, now here's just another example. This is serum uric acid levels of 267 male blood donors. And we can see that 2 men had the lowest interval is 3 to 3.4 milligrams per deciliter, and 2 men fell in that interval. That's 0.8%. If you just divide 2 by 267, you'll get 0.8%. And then there were 15 that fell in the interval of 3.5 to 3.9 milligrams per deciliter. That's 5.6 of the men in the sample. And then we have this cumulative total. It's just the 0.8 plus 5.6 is 6.4, which tells us that there were 6.4% of the men, which is 17 divided by 267, had a uric acid level of 3.9 or lower. So it's like that. And you see by the time you get to the end, this is the highest. There were 3 men who had a serum uric acid level between 8.5 and 8.9. And since it's the highest, then of course 100% had a uric acid level of 8.9 or lower. So that's another example of a frequency table. Okay, so now the frequency table is actually a tabular way to summarize your data, not graphical. But now we're going to move on to some graphical methods. First would be a histogram. So a histogram, the y-axis is the vertical axis, and that will indicate the frequency or percentage of observations. And then the x-axis will be like the categories, like the interval widths, kind of like what we saw in the frequency table. So the height of the bar tells us the frequency, and the x-axis is where the values of the variable that we're actually displaying are. So histograms are used for continuous variables. For example, we could do the uric acid level or the baby's birth weight. And in fact, let's look at here's one that is the baby's birth weight. This is the same data before, and you'll notice like these intervals actually are the same as what we saw in the frequency table before. 29.5 to 69.5 is the first interval. And so normally in the histograms that I'm used to, they have these bar widths are equally spaced, and then the height just corresponds to the frequency. This one is a little more fancy. You can tell that a statistician made this histogram because here on the y-axis it's frequency divided by the length of the group interval. In other words, so in that first interval we had 5 babies, and so but the way that he defined the height of the vertical axis was 5 divided by the difference of 29.5 and 69.5, which I believe is 40. So 5 divided by 40. That's how this height is obtained, and etc. So here it's a little fancy and unusual. I probably should not have used this example. Usually this is just frequency, and then you have your bars or different intervals. So usually the y-axis is just the number that fall in that interval. And so here we can see, but like I said, this is the same birth weight data displayed instead of the frequency table. Here it is summarized using a histogram. And so you can kind of see that most of the babies fall in here around 120 or so. There are some low outliers. Remember that real light baby down there, and some higher birth weights. So it's a good way to just quickly visualize the distribution of your data. You can look at this and kind of understand how the birth weights are distributed very quickly. A picture is worth 1,000 words, as they say. Now here's another histogram. Now don't even have what the variable is, but this is kind of a typical normally distributed variable, whatever it is, and it looks like the mean is going to be around 17 and a half, something like that. We'll be talking about this a lot more in a few minutes, but you can quickly, if you make a histogram of your data, you can really get a quick visual of the distribution of whatever the variable is that you're looking at. So the next type of graph that we're talking about is bar charts. So the different bars on the can represent different groups, and the x-axis could be a category. If, for example, if we wanted to graph the heights of males versus females, we would have 2 bars. One represent the average height of males, and the other average height of females would be one thing. Before and after is a common way to show bar charts for whatever variable that you're graphing. So in other words, the y-axis is some measure like the average, and then the x-axis going across horizontally are the different categories that you're graphing. So let's see a couple examples. For a continuous variable, maybe this is something like glucose, serum glucose, and I should have labeled the units, what milligram per deciliter. And maybe treatment A is insulin, and treatment B is metformin, something like that. And maybe we put these patients, these diabetic patients, for an example, on the different treatments, and we take their fasting glucose, and this is the mean. You can see the 2 means. So A has a little bit lower mean glucose than B, and these are called error bars. Maybe it's like plus or minus 1 standard deviation, which will give you a feel for how much variability there is around the mean. We're going to talk about standard deviation in a few minutes. So this is a bar graph where we have a continuous variable that we're graphing for different categories, in this case treatments. So it kind of gives you a visual. You can compare the 2 treatments, mean glucose value. But we can also use bar graphs for categorical variables, like if we did a survey and said, what's your favorite type of movie? 4 people said comedy, 5 people said action, 6 people said romance, 1 said drama, 4 said sci-fi. So here's a bar graph of a categorical variable. And the height is just a frequency for each of the different categories or types of movies in this case. So maybe it would be nice to review if I ask, going back to our levels of data measurement, what kind of variable, so the name of the variable is type of movie, and here you see the different categories. I could ask you, okay, what is the level of data measurement for type of movie? And your choices are, remember, continuous, dichotomous, ordinal, or nominal. Okay, I can hear you answering over there, and everybody got it right. The answer is nominal. Why? because type of movie can assume these categories: comedy, action, romance, drama, sci-fi. Okay, so I asked myself, first of all, is it continuous or categorical? Obviously, these values are not a continuous number, they're categories. So, okay, it's not continuous, it is categorical. And then I asked myself first, are there only two levels of data measurement or more than two? So here we have more than two, which says, okay, it's not dichotomous. Now our choice is between ordinal or nominal. Um, so now I ask myself, do these categories have some inherent order, or are they just names? If they have an inherent order, they would be an ordinal variable. But if they're just names with no inherent order, then it's a nominal variable. And what we have here, we have no inherent order as far as I can tell. So this type of movie would be considered a nominal variable. Just wanted to review that for levels of data measurement. So that's bar graphs. We saw how to use bar graphs for both continuous variables, for example, to show the mean serum glucose for two treatments, or we could also use it to display the frequencies of different categories, like with these favorite types of movies. Okay, another type of graph is what's called a box and whisker plot. Um, so you can see here, like maybe it's similar to a bar chart in some ways, but it gives you a lot more information, really. Here we have two distributions. We could say, just for the sake of, to give it a concrete example, that maybe this is serum glucose again for treatment A and treatment B. And so we can see here the box, this is the box, these are the whiskers. Sometimes they just call it a box plot, sometimes box and whiskers plot. Those are synonymous. And so the box itself, the top of the box is a 75th percentile, meaning if I sort all of the values that I'm graphing from lowest to highest and take the 75th, the one that's 70% of 75% of the way towards the highest is the 75th percentile, as opposed to the highest value, that's the 100th percentile. Lowest value is the first percentile, right? And if you rank them from lowest to highest, and the middle value is the median or the 50th percentile. Now in this case, you see, so the line is the median or the middle one, and then also the dot is the mean. And we're going to talk about these measures of central tendency in just a minute. But what I have here is actually what's called a symmetrical distribution, just to kind of foreshadow what we're going to talk about. The mean and median are the same. The 75th and 25th percentile are equally distant from the median. Everything is nice and symmetrical here. As contrasted with this box plot over here for group B, it's not symmetrical, right? You can see that so here we have the 75th and 25th percentile, and the median or middle 50th percentile is not exactly in the middle between these two, the value of it. And the mean is not the same as the median like it was in the group A. So this would be an asymmetrical distribution, specifically a right skewed or positively skewed distribution, because we have some really high outliers, and the mean is pulled up with those high outliers. So this box plot also shows outliers. And in this case, when you have outliers, then the end of the whisker is the 90th percentile, and the end of the lower whisker is the 10th percentile, etc. So a lot of information that you can get from the box and whisker plot. Okay, so now we've talked about tabular and graphical ways to summarize your data. Next, we're going to talk about some different descriptive statistics that you can use to summarize your data. First, we're going to talk about some measures of central tendency, and these are the ones most of you have heard of, I'm sure. The mode, median, and mean. So first, the mode. The mode, giving some sample of data, the mode is just the most frequently occurring value. And there can be a tie, like if some values have occurred the same number of times, like 2 occurs 4 times and 10 occurs 4 times, then they're both the mode. The value 2 and the value 10 are the mode. It's called a bimodal distribution when that happens. So let's have just a real simple example to show you how to find the mode. Here are the numbers 3, 1, 2, 1, 4, 2, 1, 3, 1. So that's our little sample of data, and we want to find the mode. So a way that you might start, you could just sort them from lowest to highest here, so it's easy to count. And we see we have 4 1s, 2 2s, 2 3s, and a 4. So the most commonly occurring value in this sample of data would be 1, because it occurs 4 times. And No other value occurs as many times. So 1 is the mode in this sample of data. So now let's do the median. And as I mentioned, the median, if you sort from lowest to highest, the median would be the value in the middle. But sometimes if you have an even number, there is no exact middle, as we'll see. So you have to, first, when you want to compute the median, you have to ask and find out if your sample has an even or odd number of observations. So here's our sample of data again. So again, computing the median, I would first sort from lowest to highest, and then find the middle one. So in this sample, it looks like, so we have, if we see this 2, it's bigger, telling me that that was the median. And how do I know it's the median? Well, when I sort them from lowest to highest, there are 4 values below it and 4 values above it. So that is the median. It's the middle observation. The median is 2 for this sample of data. Now here's another different example, and we're going to compute the median now on this sample of data. So again, start by sorting from lowest to highest. And then, so I've got 2 that are big this time. What's that mean? Well, look, so suppose I say, okay, is this the median? Is this 2 the median here? There are 3 below it and 4 above it. So no, that's not the median. It's not exactly in the middle. How about this 3 then? There are 4 below it and 3 above it. So no, it's not exactly in the middle. So apparently there is no single value in this data set that is exactly in the middle. The reason is I have an even number of observations. So what I have to, these are like the 2 in the middle, and I have to take the average of these 2. So the average of 2 and 3 is 2.5. So the median for this sample of data would be 2.5. When you have an even number of observations, you have to find those 2 that are in the middle and then get the average of those 2. Okay, so now we've talked about median and mode. Probably the most commonly used measure of central tendency is the mean. And as you probably know, the mean and average are synonymous, and we obtain the mean or average by just adding up all the observations, values, and then dividing by the number of observations. So in this little example, we have, these are our sample of data, and we take all those values and add them up, and they add up to 18. And if you count, there are 9 values, so 18 divided by 9 gives me a mean of 2, just the average. Now, just for a moment, I just want to kind of talk about statistical notation just so you can have some familiarity with it. I mean, it's not something that I'm going to really emphasize, but I just wanted to let you know about how it works a little bit. So you probably know that n is often used in statistics to denote the number of observations. So if there are 10 observations in our sample, we have n equals 10. And then when we're making formulas that show how to compute things in statistics, we denote all of the observations in a sample of data with like values of x, x1, x2, x3, blah blah blah, up to xn would be how we use notation to represent the values in a sample of data. And then we can say, okay, the realized values of these would be, suppose we're measuring serum glucose in patients that come through the door fasting glucose. And so that we're going to get 10, or in this case, let's say 5 patients' serum glucose levels. So the first one is 74, the second patient is 92 milligrams per deciliter, third is 67, fourth is 84, and fifth is 103. So in this sample of data, we could say x1 equals 74, x2 equals 92, etc. Xn is x5 because we have a sample of 5 in that example, and that was 103 for the 5th patient, the last patient. So that's some statistical notation. So now that we've got our 5 x values and we measured them, this right here says this is the sigma, the capital sigma, and this symbol right here, what this indicates is that sigma indicates to add or sum. So this little formula here says to take all of the x values from 1 up to n and add them all up. Add up all of the x values from 1 to n. So if we were to take this symbol and to actually execute it and execute the computation, it would look something like this. The sum is, the notation for the sum is here, the sigma, add them up from 1 to n, all the values. So xi is the subscript. Let x be 1, and add that to, and then move x up to 2 and x up to 3, x up all the way until you get to x of n, which in our sample was 5. So then we could take this and write it another way as x1 plus x2 plus x3 plus x4 plus x5. Then substitute the actual observed values for these 5 observations that we just saw before. These were the 5 serum glucose values. And then when we add them up, we get 420 for the sum. Okay, so I'm going somewhere with this. So now this is the formula for the sample mean. X bar equals the sum of the observations divided by the number of observations. Okay, so this was the part that we just did in the previous slide where we added them all up and got 420. And then, so as we see on the next slide, when we divide the 420 by the number of observations, we get a mean serum glucose level for that sample of 84 milligrams per deciliter. So I just wanted to show you, like intuitively, you already knew how to compute the average, but if I were to give you this formula right here and say to do it, oops, you probably wouldn't have known how to do it. But hopefully now you kind of get a feel for how this statistical notation, this formula, translates into the actual computation. Just wanted to give you a feel for that. Because in statistics, we have to be able to communicate that, that's a very simple example, the mean, but we have to be able to communicate some very complicated, sometimes, computations and probability distributions, etc. So we have our own little language, our own little set of symbols and formulas and everything that we can use to tell another statistician how to do the methods, how to execute the methods. So I just wanted you to see a very simple example using the sample mean. Okay, so those were the 3 measures of central tendency, which tells us like what is the middle of our distribution. We saw we could use the mode, we can use the median, or we could use the mean. Those are all different ways to kind of tell what is the middle of the distribution of the sample that we're looking at. Now, another thing that could be of interest is to tell how much variability there is in the sample, how much spread or heterogeneity, different words. Is it consistent from person to person, the serum glucose, for example, or does it vary a lot from person to person? So how might we quantify the variability of a distribution? So here are some different ways that you can do it. You could use the range, the variance, standard deviation, or percentiles are some commonly used ways to quantify variability in a distribution of data. So let's talk about some of those. So first, the range is probably the simplest. It's very easy. The range is just going to be the difference from the largest and the smallest observations in your sample of data. So if we go back to our glucose example here, we see that the glucose, here they are. So we might again sort from lowest to highest. And we see that 67 was the lowest and 103 was the highest. And the range is simply the difference between those. So 103 minus 67 is 36. So for this sample of glucose data here, the range is 36. Now that's a nice, simple, intuitive way to quantify the variability in the sample, right? It's easy to see the difference between the biggest and the smallest. That's the range. But what is the downfall of this measure is that only 2 of the observations in our sample got a vote. And everything in between, well, we know what the extremes are, but we don't have any feel for everything in between. Are they very tightly clustered and not much variability, or are they all over the place? All of those values in between the extremes. Remember, with the mean, every value contributes to the mean, right? You added them all up, all of the values in your data set, and divided by the sample size. So with the mean, everybody gets a vote. Everybody contributes to the sample mean. So maybe it would be nice if our measure of heterogeneity or measure of variability, if we could come up with some kind of statistic that also every observation gets a vote, as opposed to the range where only the 2 extremes get the vote. So let's think about how we might do this. I was thinking about this and, just trying to figure out a way to do it myself. And what I came up with is this. Here's the statistical notation. And by the way, don't worry about this because as you'll see, it's meaningless. It's no good. But I just want you to kind of think about this. How could we measure the variability in our sample of data? This is what I call Joe's D statistic that I came up with. And again, it turned out to be worthless, as usual, as most of my ideas are. But here we have the notation for Joe's D statistic. And so the way that you would execute this formula here is you take every observation in your sample of data, subtract it from the mean, and then write down that difference from the first observation going all the way up to the last observation. Get all of those differences from the mean. So then you get all of your differences from the mean and add up those differences from the mean and divide by your sample size. So it's a very, it may sound, I may have you confused at this point, but it's a very simple statistic. It's just the average difference from the mean, isn't it? We take every observation's difference from the mean and add up all the differences from the mean and then get the average difference from the mean. So this Joe's D statistic is simply the average distance from the mean, or average difference from the mean, however you want to think about it. So I took my new statistic and I was all excited because I had come up with my new measurement for variability, and I thought I was going to be famous and have my own little statistic named after me. And so I started to use this thing. Let's see what happens. So suppose I take it and apply Joe's D statistic to that same glucose data as before. So we saw before that the mean was 84. So if we go and we apply Joe's D statistic, the first value is 74. Remember, so 74 minus the mean minus 84 is going to be negative 10. The next value is 92. So 92 minus the mean of 84, it's going to be 8, etc. 67 minus negative 84, negative 17. Oh, one of the values was 84, was the mean, so that difference is 0. And then the last one was 103. So 103 minus 84 was 19. So here are my 5 differences from the mean. Divide by 5 because that was the sample size. So now I get the average difference from the mean. And oh, the average difference from the mean was 0. Huh. Well, that's weird. So the average difference from the mean is 0. And then I thought, oh, that was just a fluke. And I tried it on, a whole bunch of different samples. And guess what? Every single time, the average difference from the mean is always 0. And I thought about it. I was like, well, does that make sense? Every single value, any sample of data, the average difference from the average difference from the mean is always 0. Huh. Well, that's kind of an epiphany I had. Like that, maybe that's makes sense that the average difference from the average is always 0. Anyway, think about it and let me know. But try it on any sample of data, and you'll find that the average difference from the mean is always 0, which means that my statistic is not informative at all. It's totally worthless. Joe's D statistic, the average difference from the mean, is always 0. So it doesn't tell us anything about the variability around the mean. So I have failed in my attempt to come up with a new statistic to quantify variability. Now, what's the problem with Joe's D statistic? The average difference from the mean is always 0. Well, how could we maybe fix that? Well, a very simple way. What if we, instead of the average difference from the mean, what if we took that every difference from the mean and used the absolute value instead of the actual value? Um, and so this would be, absolute D, the average absolute difference from the mean. So you see here, it's like take every observation 1 through n, subtract it from the mean, take that value and take the absolute value. In other words, if it was negative 10, it becomes a positive 10. And then add up all the absolute values of the difference from the mean, and then get the average of that. Would that work? So let's see. If we try it on our glucose data, you see here 74 minus 84 was again negative 10, but we take the absolute value and it's a positive 10. And we get all of those differences from the mean. The negative 17 becomes a positive 17. Add up all the absolute values of the differences from the mean, and then get the average. And it was 54. So it wasn't 0. In other words, so this D absolute, it works. It quantifies the variability. It's not always 0 like my statistic was. So that's one way you could do it. And what did we do? Instead of using the average difference, we took the absolute value and got the average absolute value of the difference. And that works. That quantifies the variability. But then I discovered that my idea has already been taken. I think it's called the Manhattan distance, but somebody already had that idea as a way to quantify the variability in a sample. And so that's one way you can do it, but it's actually not the most common way. The most common way would be the variance and or standard deviation. The standard deviation is just the square root of the variance. So if you know one, you can go back and forth. So statisticians have determined that using squared deviations from the mean is actually the best way to characterize the spread of your data, particularly well when the distribution is a normal distribution, as we're going to talk about later. So, but doesn't that solve the problem kind of in a similar way as taking the absolute value? Because if I have negative 10 and I square it, it becomes 100, so it's positive. If you have a negative difference from the mean and you square it, then it becomes a positive. So it's just kind of a different way. Instead of taking the absolute value, they just square the differences from the mean. Add up all of the square differences from the mean as a way to quantify the differences, the variability around the mean. So here's a formula for the variance. This is the formula for the sample variance. We take all of the differences from the mean for the first x value 1, take that value and subtract it from the mean, get that difference and then square it, write that square difference down. Now take x up to 2, the second observation, subtract that value from the mean, square that second value's difference from the mean, write it down, and then do that all the way up to the last observation. Get all of the squared differences from the mean. And then you're going to divide that, add them all up, all the square differences from the mean to obtain what's called the sum of squares, and then divide it by n minus 1. And maybe you're thinking, why is it n? Why isn't it n? Why isn't the average square difference from the mean? Why is it n minus 1? Well, that's kind of beyond the scope of this class, but if you divide by n, that's called the population variance. If you divide by n minus 1, it's called the sample variance. And it's just been shown that for a sample of data that has been taken at random from a larger population, that this estimate dividing by n minus 1 is actually more accurate than dividing by the sample size. But you don't need to know that. But in case you were curious, and I had to write that proof long time ago in my mathematical statistics class. And I can't remember how I did it, but I'm sure we could find it if we wanted to, and prove it to ourselves that the sample mean is a better estimator than the population mean. But anyway, I've digressed. Back to the sample variance. So as we saw, the components, the numerator is the sum of the squared differences from the mean. So how do we compute that with an example, like with our glucose data? Remember 74 minus 84 for the first observation's difference from the mean. That's 10, or negative 10. And then we square negative 10 to get 100. So that's the first value squared difference from the mean. And just do that for all 5 values. Get the difference from the mean, square that difference, write down the squared difference. And then we just, in the numerator of that variance, we add up all of the squared differences from the mean, and then divide it by 1 minus the sample size, or I'm sorry, the sample size minus 1. And so for that sample of glucose data, the sum of the square differences from the mean is 814. We had 5 observations, so we'll divide it by 5 minus 1 is 4 to get a sample variance of 203.5. So that's the sample variance for that for those 5 glucose values. Okay, so the standard deviation, you've heard of it, I'm sure, is the most commonly used measure of variability for a sample of data. And all you do is you take the variance that we just saw and get the square root. So that's what this formula is. Everything under this radical sign is just the variance. So after you've computed the variance, if you take the square root, now you have the standard deviation. And why is the standard deviation such a popular method? Well, for one, it puts your values back into the original units, because when you're computing these square differences from the mean, all of the units get squared. So it would be like milligrams squared divided by deciliter squared or whatever for the glucose values. But then we take the square root of all that, and now we're back in our original units. So if we take that 203.5 sample variance that we computed earlier and get the square root of it, it becomes 14.27 milligrams per deciliter, would be our standard deviation for that sample of data. Okay, so so the standard deviation is the most commonly used statistic to quantify the variability in our sample. So now I want to kind of digress a little bit and talk about statistical notation a little bit more. And the thing that's kind of most confusing to students who are first learning about this stuff is this distinction between population parameters and sample estimates of the population parameters. It's an abstract but very important concept, actually. So a population parameter, the population is like the big population. And what we do in statistics generally is we cannot measure every single unit in the population. So what we do instead is we take a sample from that population, and we actually measure the values in the sample. but we're trying to make inference back to the larger population. Now so the population parameter, like the mean height of all men, could be a population parameter, but we don't have the time and resources to measure the heights of all men, say in the United States. So what we do is we try to take a sample of men and we can measure their heights, and we use that as our best estimate of the population of all men. So the sample estimate is trying to estimate the population parameter that we don't know, and we never will know because we just don't have the time and resources to measure it. And it's an abstract concept anyway. I mean, so what is it? Okay, maybe it's all adult men, 18 and over in the United States. Well, all the time men are turning 18 and men are dying, so our population is kind of changing all the time. So if I did try to measure the height of all men in the United States, 18 and over, by the time I finished, it would be a little different because some men have turned 18 and some have died, and things change. So it's kind of an abstract concept anyway, this population parameter. But you can see why it might be of interest to know what is the average height of males. That could be interesting. And so, and that's how statistics works, is we take our sample and we use information in that sample to make inference back to a larger population. That's kind of the whole purpose of statistics. Okay, so here's a little table showing you like the statistical notation for the population parameter and then the sample estimate of that population parameter. For example, the mean population of all men, the mean height of all men in the American population, all adult men, would be represented by the formula mu. That's the population mean height. And then, we get 27 men and we measure their heights, and that average height is x bar. We can compute x bar. It could be also mu hat just to make it confusing. There are multiple ways, but usually x bar is the statistical symbol for the sample mean. So if we get that and we compute, it's like, I don't know, 68 inches. That is our sample mean. That's our best guess at this population parameter mu, but we don't actually know mu. But X bar is our best guess, assuming that we have a representative sample of the population, right? So that's the mean. The sample mean is X bar, the population mean is mu. Same for standard deviation. It's got a sample estimate notation and a population parameter notation symbol. So the commonly used is S for the standard deviation, or it could be this Greek sigma hat. Sigma hat. If you take the population parameter sigma, that's the representation of the population standard deviation. If you put a hat on it, then it becomes the symbol for the sample estimate, which is a simple way. But depending on what book you're using, they might use a different symbol to make it all the more confusing for students trying to learn this stuff. And then the variance, as we saw, that's just the squared, the standard deviation. If you take the square root of the variance, you have the standard deviation. So sigma squared is the symbol used for the population variance. S squared would be a symbol that could be used for the sample variance. Or again, we can just put a hat on sigma squared and it becomes the sample variance. But I'm not going to ask you questions about this, but I just wanted you to know about this because it's very confusing in statistics, this distinction between a sample estimate and the population parameter that we're trying to estimate. You need to kind of understand that there's a difference. The sample is something that we can actually quantify. We have our sample, the data, we have it, we can compute the mean of 84 milligrams per deciliter. But we cannot compute the mean serum glucose of all people in the United States, for example. It's just the resources aren't there, but we would like to know, we would like to estimate it. We can do that. We can pull our sample of 5 and compute 84, and that's our best guess at this population mu. So that's again how statistics works, is we have our larger population and maybe we were interested in estimating mu, the population mean. So what we do is we pull a random sample from that population and we actually measure their values and compute the sample mean. That's our best guess back to the population mean. And the population sample size is often denoted by a capital N, whereas the sample size, the sample that we pull from the population and measure values on, is a small case n. So here's just kind of showing you, like, we have our large population and maybe we pull 5 subjects and measure their glucose, so n equals 5. Compute x bar was 84. that's our best guess as to the population mean. If we pull another sample of, say, 10, and measure that, their serum glucose of those 10 patients, random sample from the larger population, it probably wouldn't be exactly 84 the next time, would it? Maybe it's 82 or something else. Every time we pull a new random sample from our population and compute the mean, probably we'll have a different mean just due to random sample variation. So that's the thing, is we never know the population parameter we're trying to estimate, and we realize that it's subject to random sampling variation or sampling error. So that's important to know in statistics. And sometimes we want to quantify like how much uncertainty there is around our estimates. Those are the kind of things that we'll be talking about later in this semester. But now just a little feel for how sampling works when we're sampling from a larger population. Okay, so now we've alluded to the normal distribution a little bit. What is a normal distribution? It's a probability distribution that's been found to describe many naturally occurring phenomena when you're dealing with a continuous variable. So the normal distribution is a probability distribution of continuous data. Remember what continuous means from the beginning of this lecture, as opposed to categorical. You wouldn't normally use the normal distribution to describe categorical data, although under some contexts they sort of do. But anyway, not to confuse you, consider the normal distribution to be applicable only to continuous data. And so if you know that data are normally distributed, you tell me the mean and you tell me the variance or standard deviation. Remember, I can go back and forth. Just take the square root of the variance and I've got the standard deviation. So if you tell me the mean and variance and you tell me it's normally distributed, I can precisely draw the histogram. See, this is like a histogram of the data. So here we have, what do we have? We have 4 normal distributions here, okay? And this is the probability, or you can think of it as like the frequency. Remember the height. So these are like histograms, okay? And you can see like we have 3 normal distributions here where the middle, the mean, is 0. You see over here it tells you like for each colored one, the distribution, it tells you what was the mean and what was the variance. Remember, sigma squared is the variance and mu is the mean. So we have these 3 where the middle is 0, the mean is 0. And then, but we have this one down here that's shifted. It looks like the mean is -2. See here? The mean is -2 because the middle is shifted down 2. Whereas the other 3, the middle is 0. So as we talked about before, for our measures of central tendency, the mean tells us what is the middle of the distribution for a normal distribution. So we see that for 3 of these distributions here, what is that, brown, green, and blue, for those 3, the mean is 0. So the middle of the distribution is 0. As opposed to this purple one, the middle is -2. So that's how the mean quantifies the middle of the distribution. And then the second parameter you see is the variance that describes the amount of variability around the mean. So if we compare these 3 that have the mean of 0, we can see that this brown one is very tight around 0. Like most of the values are very close to 0. As opposed to this blue one, like some of them are way up here at 5 and some are way down here at -5. The most common, the mode would be 0, as is the mean. Most of them are close to 0 or somewhere closer to 0, and it's some way extreme here. But if we just look at these histograms of the orange or brown it is compared to blue, we see a lot more variability around the mean for the blue distribution compared to the brown distribution. And that's quantified here statistically with our variance. The variance of the brown one is 0.2 compared to the variance of the blue one is 5. So that's like a 25-fold increase in the variability, right? A lot more variation around. The average is 0 for both of them, for all 3 of these. But we see a lot more variability around the mean for the blue compared to the brown. And then the green one is kind of in the middle. It also has a mean of 0, but its variability is, the variance is 1. So it's somewhere in the middle in terms of variation. So that's how those 2 different measures, though, the measure of central tendency and the measures of variability, and specifically like the mean and the variance, apply to a sample of data. So we can kind of look at these graphs, these histograms, where the height represents how many. So like here, like almost all of them are close to 0. That's why this peak is so sharp. the histogram says like most of them are around 0. Whereas here you see like, the most common one is 0, but there's a lot more variation around 0. So we know it's a normal distribution if we know the mean and we know the variance. We can precisely draw this histogram, and so we can get it. We have these statistics that quantify the center of the distribution, the mean, and the variability around the mean, the variation, variance. And we can see it both with the statistics here and we can see it in the graph. So those tell the same story, just different ways of telling the same story. Okay, so now the normal distribution. So if I know that a distribution is normal, we have a normal distribution, then we know that the values, the individual values in that sample, 95% will fall within 2 standard deviations from the mean. And so if 95% fall within 2 standard deviations of the mean, and we know that this distribution is symmetrical, right? Like here's an example. Here's our normal distribution, and the mean is right in the middle. Everything's nice and symmetrical. It's a mirror image on this side of the mean and that side of the mean. And here's our 2 standard deviation units below the mean, 2 standard deviation units above the mean. So if I know 95% fall within 2 standard deviation units of the mean, that means that 2.5% of the observations fall above 2 standard deviation units from the mean, and 2.5% fall below 2 standard deviation units from the mean. So this is a normal distribution, and we know a lot about the normal distribution and how it behaves, and it's used a lot in statistics. That's why it's always nice when you have a normal distribution. It makes everything easier. But it's not always the case that you have a normal distribution. In fact, you can have asymmetrical distributions, like this is a left skewed distribution, where we have some kind of low outliers down here. And you see it's not a mirror image anymore. If we try to draw a line down the middle, there's not a mirror image on the left and right. This would be called a left skewed or negatively skewed distribution because the longer tail comes off to the left, or the negative side of the number line, right? But more commonly encountered is a right skewed distribution where we have like really high outliers. So the tail comes off to the right, so it's right skewed or positively skewed because this is the positive end of the number line. And like I said, this is a more common situation because often a lot of our measures are truncated at 0. They can't go any lower than 0, but they can go really, really high. Like length of stay would be one where you have really high length of stay, or lab values. You can't have a cholesterol less than 0, but you can have a really, really high cholesterol. So a lot of biomarkers and lab values are right skewed, meaning that you have a long tail coming off to the right for the high values, the high outliers. And so in those cases, you don't have a normal distribution, which is so it's not going to be well behaved and it's not going to be described all nice like this is. It doesn't. So we can't compute the 2 standard deviations and say that 95% of the values fall within 2 standard deviations if we have a right skewed distribution. These high outliers will pull up the mean, as we'll see, and they're also going to really pull up the variance or standard deviation. So those parameters that describe the normal distribution so well, they don't work as well for a right skewed distribution. But to review, so the normal distribution is symmetrical, as opposed to if it's not symmetrical, that means it's skewed either to the left or to the right. So now what we've just talked about are 3 different ways to measure characteristics of a distribution. The location or measure of central tendency, examples are the mean or median or mode. Those are all 3 different ways to measure the location or central tendency of a distribution. The next one is characteristic is the variability. We saw that we could use the standard deviation or the variance or the range to describe the variability in a distribution. And then a third one is symmetry. Is the characteristic of symmetry, is the distribution symmetrical or is it skewed? And there is actually a skewness statistic that you can compute that quantifies the degree of symmetry or asymmetry, but we're not going to talk about it in this class. But those are just the 3 commonly the common characteristics of interest of a distribution. What is the middle of the distribution? How much variability is there around the middle of the distribution? And is it symmetrical or not? And in fact, in statistical theory, those are called the first 3 moments of a distribution. The first moment could be thought of as like the location, the second moment is the variability, and the third moment is the symmetry of the distribution. But that goes way beyond what we need to know for this class. So now let's just see some examples, very simple, silly examples. You see generic with no labels, but maybe let's say instead, well, suppose what we're looking at here is the height, a histogram of the heights of females and males. So here on the x-axis, you can pretend that it's like height. And then remember on the y-axis of a histogram, we have the frequency. So maybe, I don't know, this is 68 inches is the average for males. And just to make something up, like 60 inches is the average for females. So if I show you this and I labeled it, I would label it with male over here and female with numbers and things. And I asked you like, okay, compare the distribution, or I'm sorry, compare the location of the two. Compare the location of males' heights to females' heights. You could look at this and say, oh, on average, males are taller than females because the middle of their distribution is higher than of males is higher than females because they're farther to the right on the number line on this x-axis going across here. So in terms of location, the males here on the right have a higher height than females. What about the next one would be variability. So, we could compute the standard deviation or variance and we could compare those two numbers for the variation around the mean for males compared to females' heights. But just looking at these graphs, let's see, it looks like how much variability is there around the mean for males and females? It looks like it's about the same. So the variability here and around the heights for males and females looks like it's about the same. So that's the second moment, the variability. And then the third is symmetry. So if we draw a line down the middle, is the male height symmetrical around this line in the middle? It looks like it is. And the same for females. So both of them, in this case, look like they're symmetrical. So to summarize those three characteristics, location, males have a taller height on average. That's the first characteristic, central tendency, or location. The second, variability, it looks like they both have about the same amount of variability around the mean. Males and females have the same amount of variability around the mean because of the how much variation we see in this histogram looks about the same. And then finally, they both look like they're symmetrical. They're both mirror images around the mean. So that's the first example. Now let's look at the second example. So pretend it's the same thing. We have male heights and female heights. And so if I were to ask you about location, again, it looks like males' center of their distribution is higher. They're taller on average than females. We see that. But there is some overlap. Some females are taller than males right here. But on average, the center of the location of the distribution males average is higher than females. So that's the first characteristic, location. The second, variability. So if I look around, draw a line in the middle, there's more variability around that mean for the males compared to the females in this example. The females are more tight. The variation around that mean is more tight, less variation for the females. Compared to the males, you see more extreme, a wider variation around the mean for the males. So if I were to take the numbers and compute the standard deviation, for example, the standard deviation would be higher for males than females in this example. So that's the second characteristic, that of variability. Males have more variability around their height than females in this example. And then the third one, symmetry. In this case, again, they're both symmetrical because if I draw a line down the middle, it's a mirror image. The histogram is a mirror image on the left and right side of the middle for males. Same for females. So both are symmetrical. Now here's just an example comparing like a symmetrical distribution versus a skewed or asymmetrical distribution. Here, when everything is nice and well behaved, looks like a normal distribution. The mean, median, and the mode are all lined up in the middle. They're all the same. But if we pull this tail out and have some high outliers, and now we have a right skewed distribution because the longer tail comes off to the right side. When we have a skewed distribution, then the mean is pulled up by those high outliers. And we kind of pull the mean, median, and mode apart, and they separate. So that's a kind of a illustration of a symmetrical versus a skewed distribution. And so Like that's why when you have a highly right skewed variable that you're trying to describe the middle of, as I mentioned, the mean is very sensitive to outliers. So a real high value is going to pull up the mean a lot, but it doesn't really affect the median. If you have a sample of data, suppose we're looking at income, right? Income is often it's a highly right skewed distribution because some people make a whole lot of money, whereas you can't have an income lower than zero. So income is typically a highly right skewed distribution, and if somebody's making, $47 million, that is going to pull the mean up a lot. But it's only one person, so it doesn't really change the median much. The middle, remember, if I rank them from lowest to highest, the median is is not very sensitive to outliers, whereas the mean is very sensitive to outliers. So that's why when you have a right skewed distribution, you commonly use the median to describe the center instead of the mean. So that's why, like, if you look in, what almanacs or whatever, where they're talking about the income, it's usually reported in terms of the median income instead of the mean income, because they know that the income is highly right skewed, and so a better representation of the middle is the median for right skewed data. So let's talk just a bit about sampling. The most common and the preferable way to obtain a sample of data is what's called a simple random sample, which is just where every single unit in the population has an equal chance of being chosen in the sample. That's the ideal situation. And that's kind of what is assumed by most statistical methods, or really by all statistical methods, is that you have a simple random sample from a larger population. Actually, not all statistical methods are special methods where you wouldn't necessarily have to have a random sample, but we're not really going to talk about those for this class. So a systematic sample, on the other hand, is where you just take your whole population, or sampling frame, as they're sometimes called, and then you take every nth value. An example, maybe like I just get a phone book of everybody's names in Houston, and I'm going to take every 100th name in that phone book and use that, pull that as my sample. That's what's called a systematic sample. In a stratified sample, we might have different groups that we want to look at, or strata, they're sometimes called, the groups, and then we pull our sample from within the groups. So, males and females, we might pull a different random sample for males and females, or different ethnic groups, whatever. And the reason this is done is because sometimes if you want to make inference within, say, some minority ethnic group, you want to make sure that you have an adequate sample size to be able to make inference within those small ethnic minorities. So you might want to what's called oversample those groups and then use weighted sampling. So that's stratified sampling, where you have different random samples obtained within different groups or strata. A convenience sample is not a probability sample. It's just whoever happens to be available, right? Common, like we're just going to survey whoever's in the waiting room. That's a convenience sample. And the problem is that a convenience sample is perhaps subject to some kind of bias. It's not a random sample from the population, and maybe the reason that those people are in the waiting room is it's going to bias them, and they're different from the people who aren't in the waiting room, depending on what your target population is and those kinds of things, which we'll talk about later. But convenience samples are commonly used. Just have to be aware that they're subject to what's called sample bias. They may not be representative of the target population of interest. Another type of sampling is what's called quota sampling, where you use and we used to use this when I would do. I used to have a job where I would do surveys, like political surveys, and we would call people, and we would have to get a certain number of each gender slash age group. So it was always like the old men, the cranky old men. At the end, we couldn't. We would have all our other quotas met, but we didn't have enough men over 65, for example. So we would have to keep calling people, and if the person who answered the phone was not a man over 65, we would say, "Oh, thank you for your time, but no, thank you," and keep calling until we got our quota. So that's done just to make sure that you have a representative sample, because in situations where you don't have to respond, like a phone call, if you just take whoever happens to answer your survey, you're going to end up with sample bias, because it's known that cranky old men are less likely to respond to your survey. So it's not going to be representative of the target population because you have less old men. So a quota sample is done in order to try to assure that your sample in the end represents the target population of interest. Particularly useful when people don't have to participate, which is almost always the case. Done to avoid sample bias. But again, the statistical methods that we use assume that we have a representative random sample from the target population. And so this is done in order to avoid sample bias. If you have a random sample from the target population, then the statistical methods can work assuming no sample bias, and the only thing you're left with is to quantify the sampling error, or the random sampling variation, which we'll talk about later in the next lectures. So again, the way sampling works is that we have our target population that we're interested in making inference about. And so we define that target population by the study inclusion and exclusion criteria. Who's eligible to get into our study? Like in remember the lecture, I used the motivating example with looking at the association between oral contraceptives and cardiovascular disease. Well, we said first we have to, of course, restrict it to females, and then we might further restrict it to females between 18 and 45 years of age. Those are our inclusion and exclusion criteria. Um, in that case, just inclusion criteria. In order to be included, have to be female between 18 and 45 years of age. So if you meet those inclusion criteria, you're eligible to be into my study. And what that does is the sample that I obtain using those inclusion exclusion criteria is generalizable to a target population of all women who are between 18 and 45. So the inclusion and exclusion criteria shapes the target population that you can make inference to. And then you hope that you have it's ideal to have a random sample of subjects from the target population. And a simple random sample is defined such that each individual member in the target population has an equal chance of being chosen and is chosen independently. So those are the two ways to define a simple random sample. For a simple random sample, every unit in the target population has an equal chance of being selected in your sample, and every observation is selected independently from each other. An example where the independence would not occur is what's called a cluster sample. Like maybe I pick a block in a neighborhood, and okay, within that, and the blocks in a city maybe would be picked at random. But then when I pick a block, I'm going to go and knock on every door and ask them to take my survey, something like that. So it's a cluster sample because the clusters, in this case blocks, are selected at random. But then within the cluster, I'm gonna interview every single person and knock on the door and interview every single person. That's not random. It's a cluster. So that you wouldn't say that, you couldn't say it's a simple representative households anymore, because the households were not chosen independently. The blocks that I knocked on all the doors on, those were selected independently, but within those, the households, the individual units, or it might be the household surveys, were not selected independently of each other. They were chosen in clusters, blocks. That's just a contrast to show you what that means. So a simple random sample, every unit from the target population has an equal chance of being chosen, and is chosen independently. So that's the end of this lecture. We'll pick up now next time talking about sampling, and we'll use this information that we've talked about sampling. It's an important segue when we go into hypothesis testing. So that's what we'll talk about next time, is hypothesis testing. Thank you very much.